everyone. We're in lecture 4. It's going to be a bit of a stressful lecture in the sense that we're going to study matrix manipulations. In particular, we'll look at how rotation of a coordinate system leads to changes in the elements of the stress tensor. So let's begin. So let us first import numpy. So now let us first look at some elementary matrix operations. In particular, let us find out the transpose of a matrix. Let us find out determinant of a matrix. Let us find out the inverse of a matrix. Okay, so let us first define a matrix to work with. So let's say A equal to np dot array, and we want 3 by 3, so there have to be 3 entries like this. So I've made 3 sets of bracket. The first set of bracket is to show that it's an entire matrix. Then we have this set of bracket, this set of bracket, and this set of bracket. So each of these 3 brackets stands for rows. So let me define 3, 2, 1, 5, 7, 4, and 9, 6, 8. So let us print what A is also. Okay, so A is this 3 by 3 matrix. So now let us find out the transpose of A. So let me go over here. B equal to np dot transpose of A. Let me print what B is. So if you look at the output, in A the first column was 359, whereas in B the first column is the first row rather is 359. So we've successfully taken a transpose of the matrix A. There's another way of defining the transpose of a matrix. So C is equal to A dot capital T. So this is also a way of transposing the matrix A, in the sense that the object A has a method transpose denoted by T. Okay, so if we double click on A and go to the contextual help, it will show some of the attributes such as A dot data, A dot D type. Okay, so apart from these attributes, it also has that method of finding out the transpose. Okay, so let us go back over here. Let me in fact print C to convince you that C is in fact the transpose of A. Okay, so there is another way of checking whether two matrices, whether all the elements are equal. So suppose I've done the transpose using the two methods. One is np dot transpose and one is A dot capital T, and I want to check whether B and C are identical. So the way to do that is, so let me just put it directly in print. So print np dot all close B comma C, and it says true, meaning all the elements of B are identical to the elements of C. In fact, if I do all close B comma A, it says false, because obviously B is a transpose of A. Moreover, A dot T, this should show true. Okay, so this is how we can make checks. So this is to check whether all the elements of B are equal to C. So even if one element is not equal, it throws false. And the reason why it's called all close, so in this case we're using integers as inputs to the array. In case you start using floating point numbers, then precise equation precisely equating two floating point numbers is not something which is logical to do. Rather, the fact that a computer has a finite representation in terms of bits, so that implies that you'll always be restricted by the representation of a number. Okay, so often 0.0016 and 0.001599, so they have to be interpreted as the same number. That's why it's called as all close. And in fact, in the function all close, you can specify the uh, the tolerances. Okay, it's not showing it in the help, but in all close you can specify the tolerance. I mean, we'll look at it later on. We'll encounter this later on as well. So let us continue. Let us find out the determinant of A. So in order to find out the determinant, we must, let me create a new cell. So let me print out A real quick. Okay, so in order to find out the determinant, we must make use of the linalg submodule of numpy. So let's call it D is equal to np dot linalg dot determinant. Is it called det? Yeah, it's just called det A. So let me print D as well. So the determinant is equal to 55.000014, and you can do it by hand. You can do it by hand and you will see that the determinant is actually 55. Okay, if you take out the determinant of this, you'll find out it's not 55.000014, but it is rather 55. And this is what I just spoke about. It's because of the finite accuracy and representation of a number in a computer. Okay, it's stored in bits, and thus there will always be these small errors. Okay, so let us look at a very important property of two matrices. So let's see whether A C dot B, the determinant of A times B, is it equal to determinant of A times the determinant of B. So let us look whether this holds true or not. So let us initialize two random matrices. So A equal to np dot random dot rand int, and say we want to sample rand int from 1 to 10, and the size, let us declare it as 3 cross 3. Similarly, B will be the same thing, and the fact that you're calling it twice, it will generate a new random array. So in fact, let me print both A and B. So A and B are obviously different, and another another professional way to check whether it is different is this should be false, and it is false. So it means A and B are distinct. So let us do the following. Let us define C as np dot dot a b. So this is a way to do matrix multiplication. So the way to do matrix multiplication is the row of A multiplies the first row of B and so on. It is the proper matrix multiplication. It is not an element wise operation. Okay, it is what we have learned in school. Alright, so let me call D as the determinant of C, and let me call E as the determinant of A times this. Now let me simply check np dot is close. So if we are trying to compare two scalar floating point numbers, instead of using all close, we can use is close. So is close is typically used for comparing two scalars. So we want to compare D and E, and we give it a relative tolerance of 1e minus 5, for example. Let me directly print this. So it says true. So is close, it gives true. Let me in fact print. So let us say LHS percentage F slash N percentage D, and print RHS percentage F slash N, and this will be E. Okay, so there you go. So these are the two. In fact, let me increase the number of digits it will print. Okay, so in this particular case they are equal to a very large degree. Let me run it again. Okay, over here look at this, it is 1440.00000 whatever, and in this case it is 1439.999999, but the relative error between these two numbers is less than 10 to the power minus 5. In fact, let us print out what the relative error between them is. And the relative error will be np.abs 1 minus d upon e. So relative error is quite small. In fact, it's all the way and the last digit becomes 4. So because the relative error between these two numbers are quite small, for all practical purposes in our calculation we can consider these to be equal. Okay. Alright, so we have so far considered the determinant, we have so far considered the transpose. Let us now proceed to find out the inverse of a matrix. So, alright, so let me define, okay, let us define a random, we've already defined a random array, so let me print out that array. So this is the, not the array, the matrix. Okay, this is the matrix A. Let us now try to find out the inverse of this matrix. So an important uh, property in order to find out the inverse is that the determinant must be non-zero. If the determinant is 0, then we cannot find out the inverse. So let us do a quick check whether the determinant is 0 or not. So let us say C equal to np.lin alg, in fact let me call it small a, dot det of a, print a. So a is obviously not equal to 0. So in that case we can find out the inverse. So let me call it b. So np.lin alg dot inf of a. Let me print what b is. So b is this particular matrix, and let us do a quick check whether a times b is equal to the identity matrix or not. So let me define C as np dot a b, and let me print what C is. So if you look at this, it is 1.00 E0, 2.77 10 to the power minus 17, minus 5.55 10 to the power minus 17. So these are as good as 0. Alright. So np dot round C comma 1. So np dot round means rounded to the first decimal. So in that case, instead of having those very small numbers appearing, we round them off to one decimal place, and they do come out to be 1110000. So C is an identity matrix, and this helps us in verifying what we already know. This is quite a trivial task, but nevertheless, it instills a bit of confidence. Okay, let us do this particular check as well. There's a theorem in matrix algebra. So A inverse transpose is equal to A transpose inverse. So let us see whether this is true or not. So let us say LHS and it is equal to np dot lin alg dot transpose so transpose is not inside lin alg, it's simply outside. So np dot transpose of np dot lin alg dot inf of A. So this is LHS and RHS is equal to np dot lin alg dot inverse of np dot transpose of A. So then let us print whether LHS and RHS are equal. So here we will write np dot all close LHS comma RHS. So it says true, meaning whatever we have claimed to be true is in fact true. And these are very famous theorems in matrix algebra. Obviously they are true, but again it's just to demonstrate how we can manipulate matrices. Let us print out the LHS and RHS just for good measure. Alright, so visual inspection as well allows us to see that LHS and RHS are equal. So before proceeding, let us quickly save this file. Let me rename it to be lec04. Alright, so let us verify one more famous theorem in matrix algebra, that multiplication of two matrices is not commutative. That is, A times B is not equal to B times A. So we have two matrices A and B already, like this. In fact, let me redeclare A and B to be two new matrices. Let me copy this bit of, let me reuse that code. Alright, so A and B are randomly initialized. So now we need to check whether A times B is, whether it is equal to B times A. So let me create C equal to np dot dot A comma B. And let me create D equal to np dot dot B comma A. So now we want to see whether C is equal to D or not. So let us just simply print np dot all close C comma D, and it says false, quite obviously, because this theorem is obviously correct. So obviously the two products are different, and hence the result. Alright, so with this, let us prove, or let us write a small function to check whether a matrix is symmetric or not. So how can we do this? So if a matrix is symmetric, then Aij will be equal to Aji. So if a matrix is symmetric, then swapping the two indices makes no difference. So let us define a function called as check sim, and it will take an input as an array, as a matrix A. Okay, so inside this we'll simply check whether the transpose of A is equal to the matrix itself. So it will simply return np dot is all close A and A dot T. That's it. So let me run this cell. Let me declare an array. Let me declare a matrix. So let me make it 1 2 3 2 4 5 and 3 5 6. Let me print what a is. We forgot a bracket over here. So obviously by visual inspection we can see that matrix A is symmetric. I mean, we've made small arrays, and so we can easily have a visual check whether it's true or not. But when you're doing a computation which involves large arrays, you better make some kind of function like this. And in fact, having a function like this, you can have an automatic check whether to proceed with a certain computation or not. Suppose you're working with stresses and you know that the stress tensor has to be symmetric. So it's a good check to start off whether a stress tensor is symmetric or not. Alright, so let us pass A to the checker. So print check sim A, and it says true. In fact, I've mentioned this in one of the earlier lectures as well. A is just a placeholder. This particular A has nothing to do with this particular A. Even if I declare this as something like this, it will hardly make a difference. Okay, so it's just a placeholder. It's not a variable which is accessible to the other functions. It has a very limited local scope. All right, so let us define the double dot product. So it is defined as a double dot b, and it is in an index notation it is aij bij, and this is using the Einstein summation notation, where on the right hand side we have I which is repeated index and j which is repeated index. So uh, essentially it implies that this is actually equal to sum over I and j of aij bij. So essentially it will be something which resembles a11 b11. It will be a11 b11 plus a12 b12 plus a13 b13 plus a21 b21 and so on, all the way from I equal to 1 to 3 to j equal to 1 to 3. So let us see how to do this. And this kind of product in Python is called as a tensor dot product. So let us see what the two arrays we already have. So these are the two arrays. So let us define C is equal to np dot tensor dot of a comma b, and let us print out the value of C. So it's 169. So how do we know whether this particular sum is correct or not? Okay, so let us define sum s equal to 0 for I in np dot a range 0 comma 3, for j in np dot a range 0 comma 3, s equal to s plus a ij times b ij. Well, I've written it like this, but this is also equivalent. Okay, this is also the same thing. So at the end of the computation, let us print what s is. So s is equal to 169. So we've established what a tensor dot product is. So tensor dot product contracts two tensors into a single scalar. Okay, and this kind of double dot product is typically used in uh, finding out terms like viscous dissipation. So in fluid mechanics or convective heat and mass transfer, or rather in heat transfer, you'll find that if you write down the energy equation, you end up with a viscous dissipation term which resembles something like this: tau ij s ij, where tau is the uh, stress tensor and s is the rate of deformation tensor. So this is how the viscous dissipation is obtained, and it has the same tensor dot structure as we have shown over here. So yet another way of quickly finding out this tensor dot product using vectorized. So we've made use of two loops over here, and obviously in Python you want to avoid using loops. You want to vectorize your code. You don't want to make explicit declarations of loops. So let me just quickly show you how to do that. So simply we will first flatten all the elements of the matrix into a straight line. So the way to flatten something, so let me print out what A is. Now let me print out what the flattened version of A is. np dot nd array dot flatten. Okay, so I have essentially flattened all the elements of A. So now you can imagine if we have an if we have these two arrays, so we need to take a element wise product of these two. Okay, we need to take an element wise product of these two, and whatever we obtain using that, we have to sum over all the elements. So let me just show it. So C equal to the product of this times this. So let me in fact print what C is for your benefit. So this is what C is, and now simply I need to sum over all the elements of C. So the way I can do that is np dot sum of C, and it does give 169. So I've shown you a very efficient way of going about things. So simply the way to do a tensor dot product would have been this. So this is a vectorized way of computing the tensor dot product. So instead of having these two loops, we have written everything in a single line, and that saves time. When the matrices become really big, this is how you start saving time. So let us now proceed to find out a rotation matrix. So what is a rotation matrix? So consider rather the transformation matrix. It should be clearer. So let us consider a coordinate system xy and a vector. Say this is a vector A. Now in a rotated coordinate system such as this, so let's say this is x prime and this is y prime. So we have rotated this coordinate system by an angle theta. So we are interested to know what are the components of A in this rotated coordinate system. So let the components of A be A1 and A2 in the first coordinate system. So what are A prime? So A prime is A1 prime and A2 prime. So geometrically, this is A1 and this is A2. And this is A prime, A1 prime, and this is going to be A2 prime. So we're interested to relate the components in the rotated coordinate system with the original coordinate system. So the fact of the matter is rotation of a coordinate system should not have any bearing on the representation of A. meaning a1I plus a2j should still be equal to a1 prime I prime plus a2 prime j prime, when where I prime and j prime are unit vectors in the x prime and y prime direction. So now let us take a dot product of everything with I prime. So a1 prime is a1 I dot I prime plus a2 j dot I prime. Similarly, a2 prime is equal to a1 I dot j prime plus a2 j dot j prime, where we have made use of the fact that I prime dot j prime is equal to 0. That is, I prime and j prime are orthogonal. Alright, so what is I dot I prime? I dot I prime is the angle between this unit vector and this unit vector, that is cos theta. So essentially the first expression essentially boils down to a1 prime equal to a1 cos theta plus a2 times j dot I prime. So j is this direction and I prime is this direction. So this cos of this angle is basically sine theta. A2 prime is basically a1 I dot j prime. So this is j prime and this is I. So it is cos of 90 plus theta, which is minus sine theta. And A2, this is j and this is j prime. So this angle is obviously theta. So this will be cos theta because j dot j prime is cos theta. So essentially we end up with a representation like this. So a1 prime, a2 prime on one side is equal to cos theta sine theta minus sine theta cos theta times a1 a2. So essentially a prime vector is equal to q dot a, where q is called as the transformation matrix. Alright, so now let us encode this particular transformation matrix in Python. Alright, so we want to find out v prime. Okay, so let us define first the theta, that is the rotation of the coordinate system. So theta is equal to, so let us declare it in terms of radian directly. So 30 times, so we have to make it into radian because all these angles have to be in radians and not in degrees. So times np dot pi divided by 180. Okay, so this is the angle. Let us define q equal to np dot array. So let us do a 2D transformation first. So we need two such brackets. So one is np dot cos of theta, np dot sine of theta minus np dot sine of theta, np dot cos of theta. So let us print out what the q matrix looks like. So q is the transformation matrix. So print q. So this is what it looks like. So let us now create a vector, or rather before delving into the transformation itself, let us quickly look at some properties of the transformation matrix. So here are some properties which are quite well known from matrix algebra. I'm just pointing them out for as a refresher, nothing else. So the first property is the determinant of q is equal to 1. Second property is the transpose of q is equal to the inverse of q. And the third property is by corollary actually, Q transpose is equal to the identity matrix. So let us look at these three properties one by one. So let us check whether the determinant of Q is 1 or not. So let me define C equal to np dot lin alg dot det of Q. Let me print C. And see, the determinant of C is obviously equal to 1. And that is quite obvious because the determinant of this fellow over here is cos square theta minus of minus sine square theta. So it is 1. So it is identically equal to 1. Let us check for the second identity. So LHS equal to np dot transpose of Q. RHS is equal to np dot lin alg dot inverse of Q. So then let us print np dot all close LHS comma RHS and R tall equal to 1e minus 6. So it is true. In fact, in order to check whether this particular identity is true or not, we can make use of a function called as ones or eyes, not ones but eyes. So let me define. It's called as eyes in MATLAB, but in NumPy it is I. So let me define I equal to np dot I 2. Let me print out what I is. So I is an identity matrix. So np dot I gives you a diagonal 1 matrix. Every other element is set to 0. So let me do this directly. So print np dot all close np dot dot q comma q dot transpose, and I have to check whether this is close to I or not. Okay, so it is in fact equal to I. So this last identity we have done using the single line, and oftentimes nesting these functions may not be in the best interest for readability of the code. So when you write such a short code, it often ends up confusing the other reader. So in this particular case it's not so complicated, and so we can do it like this. But in other case it is expedient to define this as some other variable and then check this. All right, so now let us consider a having two components like this. So let a be 1 comma 3 for example. So find out a prime. All right, so the components of a prime will be equal to, so a prime will be equal to np dot dot q comma a, but we have not yet defined what a is. So np dot so a equal to np dot array. So it has to have two components. The first component is 1 while the second component is 3. Okay, so let us print out what the components of ap are. So these are the two components of ap. So the angle is 30 degree. So how does this look like? Let us try to draw this. I mean, so we have a system like this, and we have rotated by 30 degree. something close to this. And the first, it was 1 comma 3. It was something like this. So it was 1 comma 3 in this coordinate system, and it does look to be something equal in the other coordinate system. So over here it is something 2.366 and 2.09. I mean, physically it makes sense. Okay, so let us in fact do a full rotation sweep and see how the components vary. I mean to say, in a loop, we can vary this theta going from 0 to a certain to all the way to 360 degrees, and we'll try to find out what the components will be. So in fact, there will be a certain angle. There will be a certain angle. So when the coordinate system is something like this, there will be no y component. Okay, the y component is 0 because the vector is aligned completely with the x prime coordinate, and there will be an angle. So when the coordinate system appears to be something like this, something like this, so this will be y prime and this will be x prime. So when the coordinate system would have rotated by this particular angle, we would have only a y prime component which would be non-zero and x prime would be 0. In fact, this would occur also when this will be y prime and this will be x. So when the coordinate system rotates by this angle. Okay, try to draw this on your own and you'll see what I mean. So let us do a sweep of theta and find out the two components of the transformed vector a prime. Okay, so let us do that. So let us create the theta array. So theta equal to np, or let me call it theta a to signify that it's an array. So it will be np dot linspace. So 0 to 2 times pi and in steps of 100. So this is theta in radians. So let me create the vector v. Okay, let us use it. Let us use the vector a. So a equal to np dot array. Let me redefine it just for completeness. So now we have to run in a loop. So in order to store each element of the transformed vector, so basically we need to have uh, two arrays, one of which will store all the components of a1 prime for all different thetas, and one which will store all the components of a2 prime for all the different thetas. So there will be 100 values of thetas as defined in this linspace. Okay, and there will be 100 values of a2 prime as well as defined by this linspace. So let us create two empty arrays. So it is always a good idea to initialize whatever you're going to store. Instead of dynamically allocating an array, it is always a better idea to pre-allocate it in terms of zeros. So we will declare v prime 1 array is equal to np dot zeros np dot shape of theta a. It means it will create a zero array which has the same shape as the theta array. This is important because theta array and a1 prime vp, I'm calling it v, let me call it a. So a prime 1 array and theta array must have the same length, and hence they must have the same dimension as well. Okay, similarly ap2 underscore a equal to np dot zeros, np dot shape theta underscore a. So this ensures that if I change the number of elements in theta a, it will automatically change the number of elements in ap1a and ap2a. So I don't have to hard code the size of a prime 1a and a prime 2a. Okay, instead of hard coding it, I'm querying the size that these two arrays should be from the earlier declared array of theta. Okay, so now we can go in a loop. So for theta in theta a, so theta will pick up each element of theta a in the loop. All right, ap1a, and now we have to create a counter as well, because for the first loop it has to have a value of a0, ap1 0, then 2, 1, 2, 3, 4, and so on till 99. So this will be count, where I have to first define count outside the loop as 0. So ap1 count is equal to, it will be equal to, in fact let me do this, ap equal to np dot q times a, where q equal to np dot array, np dot cos theta, np dot sin theta, np dot sin theta minus of this, np dot cos theta, and we have to wrap it up with another square bracket. All right, so we have defined the transformation matrix q inside the loop, because theta is changing. So each time theta changes, the matrix q has to change as well. A is defined, a is not gonna change. So now ap is np dot qa, and now so the first element that we will save, it will be this, while the second element, it will be this. Okay, remember that the element number and the index, they differ by 1. So this is the second element, but the index is 1. Remember that this is first element, but the index is 0. Okay, so now we have stored, so when count is 0, we have stored it in ap1 underscore is 0 and ap2 underscore 0. Once this loop has executed till this point, we need to increment the value of count. So count will become count plus 1. Alright, so let us evaluate this entire cell and see what happens. Okay, so now let us plot. So plt, so first we have to import the plot functions. So import matplotlib dot pyplot as plt dot plot ap1 underscore a, and on the x-axis we will have theta. Okay, there seems to be an error. So it has to be theta a, because theta is just one of the many entries in theta a, where theta a is the array. Okay, all right, so this is how the entry, how the plot of ap1a looks like. In fact, let us plot on top of this what theta a comma ap2a looks like. All right, so it looks something like this. Let us draw the grid. let me set x levels and y levels. So now let us see. There does exist an angle where the okay, let me label this too as well. This is just to make the legends of the plot. All right. So there are points where the first component, that is a1 prime, is maximum, and that corresponds to a2 prime 0, and that happens twice. Similarly, there are points where a1 prime is 0 over here, and where a2 prime is negative minimum and positive maximum. All right. So the magnitude is maximum, and that does correspond to these four angles that we have talked about in the working out of this problem. So this is how you can do that. In fact, let us draw a phase plot of a prime, meaning plt dot plot. We will plot how a1 prime and a2 prime vary simultaneously. It's like a parametric plot. So theta is like the parameter, but I want to plot a2 prime versus a1 prime. So we will plot a1 prime underscore a and a2 prime underscore a. Oops. Ah, so this is a prime 1. One should always be careful with the variables. So it looks like a circle. In fact, let me make the aspect ratio of the plot better. So we will get first the axis, so plt.gca. Then we will set aspect ratio to be 1. Yeah. So the parametric plot does look like a circle in the sense that all the components lie on this particular circle. So if I select this particular point, all right, so it corresponds to some angle theta. In fact, let me superpose on top of this the original components. So the original components were this. Okay, so let me superpose that particular point as well. So plt dot plot. So this will be a0 comma a1, and let me put a circle, black colored circle over there. So this is the point where we have started the original vector, and as you rotate it, you will change the components a1 prime and a2 prime in accordance to this particular circle. Okay, once you rotate by a certain angle, you will reach this particular point, and these the projections will be the components of a1 prime and a2 prime. Okay, this is what it means. So now once we're done with this, we are ready to move into transforming stress. Okay, so now let me just mention how a matrix transformation looks like. So if we have a matrix sigma, so the components of sigma prime will be q times sigma times q transpose. So this is how the transformation of a matrix looks like. And so in its rawest form, this will be equal to, so yeah, it will be equal to this. So let us do this. Let us so let me define a matrix S is equal to So let me define it as 50 comma 30 and 30 comma minus 20. So typically the tensors, so there's a difference between a tensor and a matrix, but this is not the course to discuss about that, but typically it is symmetric. So let us print out what S is. So S is this matrix. Okay, so let me remove this print. Let me define what theta will be. So theta will be, say, some rotation by 30 degrees. So the coordinate system rotates by an angle 30. So 30 times pi times 180 by upon 180. So the Q, the transformation matrix will be np dot array. In fact, let me copy it from above. So now with the help of this, we can find out the transformed entity. So SP, let the transformed matrix be SP. So it will be np dot dot, and this will be np dot dot again. This will be Q comma S, and this will be Q transpose. So let us print out S and let us print out SP. So those are the transformed elements of the matrix S when the coordinate system is rotated by an angle 30. Okay, in fact, let us do the same procedure over here. Let us try to loop over all the thetas and find out how the components change. All right, so let us reuse this bit of program and let us try to convert this into a loop. So theta, first of all, we have to declare as an array. And let us define it till only 180 degree, and it will be clear why that is the case. Sorry. Okay, in order to save the different components of the transformed matrix, let us declare a few more arrays. So let us define sigma n array is equal to np dot zeros, np dot shape of theta a, and let us define tau n a equal to np dot zeros, np dot shape theta a. Okay, and again we can do the same thing. We can declare everything inside a loop for theta in theta a. So now we must indent these lines because these have to be executed inside a loop, and we must have a loop counter as well. So count equal to 0. So now let us set sigma n a count as sp 0 comma 0. That is, this particular element we are declaring as sigma n. These elements we are declaring as tau n. So these are some of the notations that solid mechanics that appear in solid mechanics. So all right, so yeah, so let us Yeah, before this we have to increment count as well. So one way of doing this is count plus equal to 1. So this is equivalent to writing count equal to count plus 1. Okay, so this is an equivalent way of writing it. So let us execute this and see whether, so there's no error. So great, we can now plot sigma n a as a function of tau n a. Let me make the aspect ratio. So it does look like a circle, but can we show it? Can we prove that it does actually have to be a circle? And the circle is not centered about 0 comma 0. It's centered about some other value. So what is that value? Okay, so let us quickly simplify whatever we were doing over here. So let me simplify whatever this is. So let us simplify this. So instead of cos theta and sin theta, I'm just gonna write C and S. So this will be C sigma 1 1 plus S sigma 2 1, C sigma 1 2 plus S sigma 2 2, minus S sigma 1 1 plus C sigma 2 1 minus S sigma 1 2 plus C sigma 2 2. This times C minus S C. Alright, so this will be equal to, so this multiplies this. So C square sigma 1 1 plus CS sigma 2 1 plus C square sigma 1 2, rather CS sigma 1 2 plus S square sigma 2 2. So this is the first element. Okay. Uh, so then the second element will be this times this plus this times this. So it will be minus CS sigma 1 1 minus S square sigma 2 1 plus C square sigma 1 2 plus CS sigma 2 2, and this will be minus CS sigma 1 1 plus C square sigma 2 1 minus S square sigma 1 2 plus CS sigma 2 2, and this will be this times this. So it will be S square sigma 1 1 minus CS sigma 2 1 plus S square sigma 1 2 plus C square sigma 2 2. So these are the components, and so sigma n prime that we have written is essentially C square sigma 1 1 plus S square sigma 2 2 plus sigma 2 1 and sigma 1 2 are equal. So this become, because we have selected the sigma to be symmetric. So this is 2 CS sigma 2 1. Tau n prime is equal to this term. So this is, so sigma 2 1 they're equal. Alright. So this is C square minus S square of sigma 2 1 plus CS sigma 2 2 minus sigma 1 1. And if you note that this element is also equal to this, okay, sigma 2 2 CS minus sigma 1 1, so it checks out. So it's symmetric as well. The transform matrix is symmetric as well. While if I call this as sigma y prime, this comes out to be S square sigma 1 1 plus C square sigma 2 2. So obviously we have made a small mistake. So this should have been this times this. This should have been minus CS. Okay. So this is minus 2CS sigma 21. So one thing to note from this is that if you add these two, sigma n prime plus sigma y prime, so this becomes sigma 1 1 because cos square plus sine square is 1, plus sigma 2 2 because cos square plus sine square is equal to 1. These two terms cancel out, while tau n prime is equal to c square minus s square times sigma 21 plus cs sigma 22 minus sigma 11. Okay, but if we just focus on this sigma n prime, so sigma n prime is equal to c square sigma 11 plus s square sigma 22 plus 2cs sigma 21, while tau n prime is equal to c square minus s. So cos square theta minus sin square theta is cos 2 theta. So we can write this as cos 2 theta sigma 21 and plus 2, not 2. So this will be half. So half sin 2 theta times sigma 22 minus sigma 11. While this can be written as cos square sigma 11 plus cos square theta sigma 11 plus sine square theta sigma 22 plus sine 2 theta sigma 21. So keeping this in mind, we can further simplify everything and we can show that sigma x rather sigma n prime minus sigma y prime upon 2 whole square, okay, plus tau n prime whole square is equal to sigma x minus not sigma x but sigma 11 minus sigma 22 upon 2 whole square plus tau square. This can be shown using these expressions, and with the help of this we can finally write down an expression like this, sigma n prime. So let us add and subtract sigma n prime. So if we add and subtract over here, so this becomes 2 sigma n prime minus sigma n prime minus plus sigma y prime upon 2 whole square plus tau n prime whole square is equal to sigma 11 minus sigma 22 upon 2 whole square plus tau square. And this essentially means sigma n prime minus sigma n prime plus sigma y prime by 2 this whole square plus tau n prime whole square is equal to whatever this is. And this implies, and this particular earlier result when we combine, so this implies that sigma n prime minus sigma average, or rather this is half the trace. Okay, so this is half the trace of sigma this whole square plus tau n prime whole square is equal to, if we call this as r square, okay, this is equal to r square. So it's clear that the locus, or rather the curve in the sigma n prime tau n prime plane will be a circle whose center is at this point, that is the sigma average, that is sigma n prime plus sigma y prime by 2. And I call it the average because sigma n prime plus sigma y prime upon 2 is, by this particular result, also equal to sigma 11 plus sigma 22 by 2. Hence I have written it as the trace of sigma upon 2, because the trace is simply the sum of diagonals, and the radius of this circle is equal to this entity. Okay, so let us verify whether that is true. Let us verify whether that is true. So on top of this plot, let me plot the center of the circle. Plt dot plot. So the x point will be half of the trace. So np dot trace of s divided by 2 comma 0, and let me mark it by a black point. Sorry. Okay, so this is indeed the center, and that is simply the trace of S, and we don't need the transformed matrix to find out the location of the center. Okay, so and the radius of this circle you can independently verify that it will be equal to this equation over here, and this particular construction is called as the Moore circle. Okay, and it helps us in identifying which will be the coordinate system in which we will experience maximum shear stress or the maximum normal stress. So on the x-axis we have essentially the maximum, another the transform normal stress. On the y-axis we have the maximum uh, shear stress. Okay, so let me label this. So the x level will be equal to sigma n prime, while the we have to put a double escape character over here, and plt dot y level will be equal to tau n prime. Okay, so this helps us in identifying the locations of the maximum uh, shear stress and normal stress. And I request you to have a look at basic solid mechanics and try to figure out all this on your own. There will be a number of problems where you're required to find out the plane where the maximum stress occurs and try to resolve it using Python. I've shown you how to do it. So this pretty much wraps up this particular lecture. And in this lecture, we have covered a whole lot of matrix manipulations, and I've shown you how it can be used to your advantage to understand matrix transformations and vector transformations. This is different from vector rotations, where you're rotating a vector. Here, we're rotating coordinate systems. And in your free time, I request you to have a look into rotation of vectors and rotation of matrices, not just the transformations. With this, it's goodbye from me. I'll see you again next time. Bye.